Hello and welcome to episode 13 of Chemistry in 15 Minutes or Less. My name is Audra and this review lesson is on chapters 6 and 7, part 6, Lewis dot structures. Now, there are 6 ways we need to learn about Lewis dot structures. Number 1, just how to do all of the main group element atoms. 2, monatomic ions. 3, simple molecules. 4, multi-atom molecules. 5, multi-bonds. 6 are called resonance structures. And 7, polyatomic. And then, of course, afterwards we will go over some exceptions. Now, as far as the first one goes, talking about atoms. These are based on the valence electrons that are available for bonding. So let's just take the first couple of elements going across: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now, lithium, being the first group, only has one available bonding electron. So, we draw it out to the side like this. Now, you can't put it anywhere that you want. And to note, there are basically 4 planes to draw it in. I'm not crossing it out. You can draw it here, 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 or here. These are basically the inner shells that you can fill, so you can only fill up one shell with this, because there's only one electron. Now, beryllium is here. Now this is where we're going to bring Hund's rule back. You can't go ahead and just pair these up, so we're just going to draw them here, here. You can also draw them there and across from each other, or up and down. It doesn't really matter where you want to put them. Next, we have boron, that has 3. Hund's rule again, they have to be away from each other. Now, carbon is pretty easy because you just put all 4 across for all 4 of its bonds. Now, nitrogen has 5 bonding electrons, which means you get 4 in, and then it's full, which means you have to start pairing up electrons. Now, you don't draw them like this, out next to each other. That's not correct. You draw them as a pair, this way. Up and down from each other, or if it's up here, across from each other, same way. Now oxygen has 6 valence electrons, which means it has 2 pairs, 2 singular. Fluorine is a halogen, which means it has 7, which means it has 3 pairs, 1 lone electron. And neon, being a noble gas, has a full valence shell. This just helps you try and visualize what they would look like. And another thing to talk about quickly is hydrogen and helium. Now helium already has a full valence shell, which is called a duet, which goes here, and hydrogen only has 1. So these two do not technically meet the octet rule because they can only have 2, which is, like I said, called a duet. Now, number 2 that we need to talk about, like I said, is monatomic ions. Now, you need to look at it through this little table here. Element, just the ion. And we're just going to go through 2 examples. Now, what I didn't mention with the first one, let me just quickly go back to it. Groups follow the same rules. So if you have, for example, lithium with 1, everything in group 1 following down is going to look the same way. You're going to draw it the same way. And that's very, very important to understand for this next thing we're about to talk about. Now let's say we have strontium right here with its 2, because it is one of the alkaline earth metals, which means it follows beryllium. It's got 2. And let's take a halogen iodine. Now, in order to draw this, you wouldn't draw the ion like this. You put the element in brackets and put the charge above it. Now, since it doesn't have a full valence shell, you don't have to draw it in here, but for some of the other ones, you will have to draw the full valence shell for the anion. And still include the charge. Now, to write them together for something like, say, ferric oxide or iron 3 oxide, what you have to do is you have to draw however many of the ions are present, which in this case it's iron 3+, and there are 2 of them. And oxygen, since it's the anion, gets the full valence shell, its charge, and there are 3 of them. It's pretty simple. We don't do as much of this as we do in the other ones. Now for 3, we're going to start getting into simple molecules. So, for a quick example, we have 2 hydrogens that are bonding. In order to draw them together, they share electrons because it's a covalent bond, so you put them together like this. To help you visualize it better, let's use some different colors. If you have, let's put this hydrogen in red, this hydrogen has this electron, and this other hydrogen is going to be in blue. They both, as you'll notice, have a full valence shell. For them as a duet, while sharing those 2 electrons. For something like chlorine, which is a halogen, chlorine tends to bond with itself because it has the 1 available electron, is very reactive. So to draw chlorine together, they share the 2 that are open, and both then have their full octet rule meeting valence shell. Now, you don't always have to draw it like this. You can draw the bond as a little dash between them, which basically means the 2 dots there, but you have to fill out the rest of the shell. We'll just do one more example. We'll bond hydrogen with chlorine. And the 2 ways you can draw it are either here, which as you can see, hydrogen has its full shell of just 2, you don't have to draw all the way around it, or you can draw it with the bond as a dash instead of as arrows. Arrows? Sorry, I need dots. It's early. Now, number 4. Multi-atom molecules. This is where we'll get into stuff like H2O, which has hydrogen, oxygen, and another hydrogen. Now to bond that together, you can do it the same way you do the other ones, where you have to make sure everything meets the octet or duet rule, having its own version of the shared electrons to have its full shell. Again, same thing, you can draw them with the dashes like this, as long as for something like oxygen you put in the rest of the electrons that make sense. Or to give it the full valence shell, because this is still worth 2. Let's do another example with methane, which is CH4, which we'll talk about when we get into organics. But methane, to draw it, you would either draw it this way, with the dashes, or giving carbon its full valence shell, because carbon has 4 available bonds, this way. Now I'm going to clear some space and we're going to do a slightly more complicated example. Now, let's say you have something that's called methanol, which we'll talk about again with organics, but its formula is CH3OH. Now, sometimes in order to figure it out, you just need to know where everything would go, how many bonds everything has. Carbon has 4, so carbon tends to be your central. Hydrogen has 1, you have 4 hydrogens. You have oxygen that has 2 available bonds. So its drawing would look something like this, if you're doing it with the dots instead of the dashes. As you'll notice, it tends to follow its formula. C has 3 H's, the O has 1, and the O and the C are bonded together because they have the most available bonds. And once again, you can draw it like this if you prefer. As you'll notice, carbon doesn't have any dots because it has 4 bonds going out, so you don't need to worry about it. As long as your drawing shows that it has a full valence shell, it's an acceptable drawing. Now, number 5, talking about multibonding, which is basically double or triple bonds. There can't be anything past triple bonds. Now, for an example, oxygen always tends to bond to itself when it's free in the atmosphere, so it's what's known as O2. Now, if you try to draw that the way we have been, you'll notice that then oxygen has 2 free electrons, which is not possible because we need them to both have a full valence shell. So in order to do that, they concentrate them in the middle in a double bond. Now don't forget they want to be as far away from each other as possible, so with these pairs you don't want to try and put one here. That's not correct. So in order to draw that in a more familiar way, you would draw it this way, still including all of the extra electrons for oxygen to double bond. Now this is the point at which a table might come into play when you're trying to figure out drawings. Also important to note, groups 16 to 18 are the ones that double bond. Now I'm just going to use the example of O2 because that's already what we have up. You'll have your element, which in this case we have oxygen, and we have 2 oxygens. How many valence electrons they have, which is 6, but in this case it's 2 times 6, which is 12. Then, how many does it need to meet the octet rule, which for oxygen is 8. 2 times 8 again, 16. And then, number of shared electrons, which basically, in order to figure that out, you take the octet rule minus the valence electrons, which means there are 4 shared, and if there are 2 electrons per bond, there need to be 2 bonds. So in order to do that, oxygen has to double bond. You can use this with other elements that make sense as well, but let's just do one last quick example without using the table of what this would look like. Let's go with something familiar. CO2, carbon dioxide. Now in order to draw this, carbon can bond 4 times and oxygen can bond twice. So, if we're drawing it this way, it'll want to double bond twice in the middle here. Oxygen will have its full valence shell, so that way carbon has its 4 bonds, and both of the oxygens have their 2 bonds. Everybody has their full valence shell, everybody's happy. Now, for the first time, I am running out of time, so I'm going to need to break this into 2 separate videos. So this should conclude part 1 of episode 13 of Chemistry in 15 minutes or less. Feel free to leave questions or suggestions in the comments below, and be sure to follow the in-video links, check out the playlist, or head over to my channel for more videos on chemistry review. And the second part will also be linked, as well as the playlist. I hope this helps, and I will see you in part 2.